Okay, so section 4, electric potential energy, which is a U. What we have here is two charged particles, positive Q and negative Q. Yes, they will exert a force on each other, but we're actually not going to look at force right now. Instead, we're going to look at what type of energy has been stored by placing these two together. So we're just going to have them fixed in space, r apart, and we want to know how much is stored. What's really nice about electric potential energy and electric potential, as we'll find, is these are objects, or these are concepts that are not vectors. So these are quantities that are not going to be a vector. So we don't have to draw pictures to figure it out. We can literally just plug and chug. So what we're going to do is we are going to find out what U is, and U is equal to K QQ over R. For the situation I have here, where they're r apart, we have a negative kq squared over r. So now when you would have them in a line or you would have them in a triangle, you would not care about the direction. You would just add them up and plug in negatives if there is a negative. So for example here, I have a q. Instead of a q, I'm going to put a big capital Q. So I have the capital Q, and then for the negative Q, I'm going to put in a negative Q. So I end up with negative KQ squared over R. All right, but let's say I wanted to compare the energy, that the change in potential energy when, I'm going to try to move this when I move this charge from here to here. Okay, so when I do that, what's going to happen is this is not something that would naturally happen, right? Because why not? Well, because, oh, nope. Let's try one more time. There we go. Because the negative Q and the positive Q, they would be attracted to each other. So naturally it would go this way. So I'm saying, okay, well, I'm going to put it over here anyway. And I want to see what the change in potential energy is. So to do this, recall that delta U, and delta anything means the final condition minus the initial condition. So I have my final condition written here. It's 2R away. I know that's not perfect. Pretend there's no space there. 2R away, but it's still the same type of charges, positive Q, negative Q, and K is still there. Then I'm going to subtract the original formation, negative KQ squared over R. So I have minus a negative KQ squared over R. And what I end up with is a positive value, positive 1/2 KQ squared over R. And you can work out that math on your own, finding a common denominator. But what I end up with is positive work because this would never happen on its own. So something from the outside had to come and move it from here to here. So work was done on the charge. Negative work would mean it would do it on its own. So if I were to compare from going from, oops, I wish it was just a little smoother, to R, so from R to 1/2 R, well, this is going to happen on its own. So I should get a negative value for work in that situation. And just recall that work is a change in potential energy. All right, next we're going to talk about the change in potential energy for charge in a uniform electric field. So I just put this here so I could easily grab it. So now if we put this in the electric field, we're going to have here parallel to the lines, work will either be done on or by the system. Here, work would be done by the system. It would just happen naturally. If I were going to move the other direction to the left towards the other plate, well, then something would have to physically move that. So it'd be positive work done on the system. But what's interesting here is that, oh, I shouldn't have uncycled. If I go up and down perpendicular to the field lines, no work is done at all. Okay. And that's that.